Hello everyone. This video is to help you understand what is required of you for your second growth project, which is called the Bacterial Growth Project. And so what this particular project is trying to emphasize is an application of how to use what we call geometric sequences. And so in general, a sequence is just a list of numbers. And what we do is we take those list of numbers and try to um, write them as a function. Okay. So for instance, if I was to take the numbers here, let's say 1, and then 5, and then 9, and then 13, and then 17, and then so on and so forth. One of the things that you see about this is that all these numbers have a difference of 4, because 5 minus 1 is 4, 9 minus 5 is 4, 13 minus 9 is 4, 17 minus 13 is 4. And so because of that, this is what's called an arithmetic sequence. And arithmetic sequences, one of the things that's true about them is that all the numbers have a common difference. And the formula for an arithmetic sequence looks like this. So you start off with the a sub 1, which is the first term in the sequence, plus, and we'll say n minus 1 times d, where d is your common difference. Okay. So if I wanted to, I could really write this and say a sub 1 is my first term, so that would be 1 plus n minus 1 times d. My d is 4 in this case. So here, if I wanted to write this real fancy, I could simplify by saying 1 plus 4n minus 4, which ends up being 4n minus 3. And so from that, if I wanted to list the first few numbers in the sequence, let's say a sub 1, a sub 2, a sub 3, meaning the 1 here is telling you which number in the sequence you're trying to get. We know that, hey, if I just plug in a 1 right here, 4 times 1 minus 3 gets you 1, because 4 times 1 is 4. Of course, here for a sub 2, we would plug in a 2 for a. And of course, 4 times 2 is 8, minus 3 is 5. And then for 3, we would plug in a 3 for n, and 4 times 3 is 12, minus 3 is 9. So you can see how these numbers here match up with what I was talking about there. So that is an arithmetic sequence. An example of what we're going to be doing here is what's called a geometric sequence. And so instead of having a common difference like the arithmetic sequence here, what we will have is a common ratio. So to kind of give you an idea of that, I'm going to make up another quick example. So let's say I started off with, let's say the number 4. And so here, I say the next number is 20, and then the next number is 100, and then the next number is 500, so on and so forth. One of the things that you'll see here is that what is common amongst all these numbers here is that if I take 20 and divide it by 4, I know that 20 divided by 4 is 5. I also know that 100 divided by 20 is going to be 5. And I know that 500 divided by 100 is 5. So here we can say, all right, well, 4 times 5 is 20, 20 times 5 is 100, and 100 times 5 is 500. So what we call this is a common ratio, because if we can take this number and divide it by the previous one and get the same number every time, we know those numbers are related in what's called a geometric sequence. And so just like how I did the arithmetic one, I can come here and also write a fancy formula for the geometric sequence, which is what this is. Okay, and so I'll do that right quick before we get into our actual examples. So here, if I do a sub n, I know that a sub 1 represents the first number in the sequence. In this case, it's 4. The r is the common difference, which is 5 we got from all of this. So we'll say that that's 5, and we just raise that to the n minus 1 power. Okay. And so please be careful not to take this 4 and multiply it times that 5. We cannot do that because if we did, we would be violating order of operations. We have to do exponents before multiplication, so we have to leave it in this form. Okay. Now, to calculate a few terms so that you can see how we get the 4 and then the 20 and then the 100, if I wanted to have the first value here, this would be 4 times 5 raised to the 1 minus 1. And of course, here we know that 1 minus 1 is just 0. And anything raised to the 0 power is 1. And so with that, we know that our final answer there would be 4. Now let's make some separation. For the second term in the sequence, the only thing that's different now is that we put a 2 here instead of 1. And of course now we know that 2 minus 1 is 1, and anything raised to the 1 power is itself. And so that's how we get 20. And then when we plug in 3, same kind of thing. That didn't go so well, but we'll clean it up. So we're back here. So now that's 4 times 5 raised to the 2. And of course we have to do 5 squared, which is 25. And of course 4 times 25 is 100. So you see how here I get 4, then 20, then 100, kind of goes along with what we're talking about here. So now that you have a general understanding of what an arithmetic sequence is versus a geometric one, you can sort of understand that when we do this project here, we are going to be doing one that is geometric. So I'm going to erase what we have here and then get into what it is that you actually need to do for this project. All right, so now that we've made some room, we can now look at the information that we're given and sort of decipher what's going on and how we need to interpret that so that we can do this project. So if you're looking at this project, the first thing that it asks you to do is determine the rate at which these bacterial, at the rate at which each bacterial culture grows. And so let's look at the first bacterial culture sample and see what's happening there. So here we see that we have 13, then 78, then 468, then 2,808, 16,848, 100,088, and I think this is wrong here, so let me correct this. This particular value should be 606,528. That's what it should be. So if we look there, what you'll see is we can start to just examine by doing what we did when we looked at the geometric sequence earlier, which is take this number and divide it by the previous one. Okay, and so if we take, let's bring our calculator in. If we take 78 and divide it by 13, see that we'll get 6. And so if we do the same thing here, if we take 468 and divide that by 78, so let's do that. You see that you'll also get 6. If we do 2,808 and divide that by 468, you'll see that you get 6. So we see that the way that this particular bacterial culture is growing here, if we verified all the others, you'll see that the common ratio is 6 among all the times that we are tracking the growth here. And so I'll just go ahead and go through the rest of them to verify. So we do 16,848 divided by 2,808, and we still get 6. And then, of course, the 101,088 divided by 16,848, that's 6. And then the last one, 606,528 divided by 101,088. And you see that all those are 6. So because of that, we know that our common ratio for bacterial culture sample number 1 is going to be 6. So now that we know that information, we know that each hour this bacterial culture has been growing in a geometric sequence sort of fashion. So our formula for just a general geometric sequence is a sub n is equal to a sub 1, which is the first term in the sequence, times r, which is the common ratio, raised to the n minus 1. And so we know our a sub 1 for bacterial culture sample number 1 is 13. We know that our common ratio is 6, and that's pretty much all we need to know. So here we're asked to determine the rate at which the culture grows in an hour. Well, that rate here is 6, because that's the common ratio, okay? And so from there, we're also asked to come up with a formula. So since we have this, we now know that our a sub n, or the numbers in the sequence, can be characterized by saying 13 times 6 raised to the n minus 1. Okay. And so once we have that, then the next thing that we're asked to do is to figure out how many bacteria will be there after the 8th hour, and then after the 10th hour, and then after the 12th hour. And so also after what it would be for 24 hours. And so we can figure all those things out. Now that we have a formula, we can use our calculators again to help us quickly come up with those numbers without us having to do a whole lot of hand computation. So I'm going to bring our calculator back, and we're going to go to the y equals, and we're going to type in this function. So this will be 13 times, and then this, and I'm going to do this in parentheses. I don't necessarily have to, but I'm going to do it for clarity here. And then 6, and then this button is raised to, and then in parentheses I'm going to put x, so I'll press this button, minus 1, and then close parentheses. And so what I have here is exactly what I need. And so now all I have to do is tell my calculator to evaluate n when it is 8, when it is 10, and when it is 12, and then again when it's 24. So just to make sure that we're on the same page here, we want to figure out what is this when n is 8, n is 10, n is 12, and n is 24, which means we want to figure out what a sub 8 is, a sub 10 is, a sub 12 is, and a sub 24. And this will tell us the amount of bacteria that will be in a particular petri dish or whatnot after the 8th hour, 10th hour, 12th hour, and 24th hour. Okay. Now I'm bringing the calculator back. We want to make sure that we can actually calculate this function for all of these values. So we go to window to make sure that that can happen. What's important to us is the x min and the x max. The numbers 8, 10, 12, and 24, all of them do not fit in between negative 10 to 10. In particular, 24 doesn't fit. So again, what we want to do is I'm going to change this from a negative 20, excuse me, I'll say negative 30 to 30. And that way I know that all the numbers 8, 10, 12, and 24 actually fit within that particular range. So once that's done, then we go to second trace, and this is the calc feature, and here we pick value. And so now when x equals pops up, that's going to be our equivalent of n here. We just type in 8, figure out what the bacterial culture amount is, 10, 12, and then 24. Okay, so for 8, hit enter, we get the this number here, which is 3,639,168. Then we do it again for 10, and we see now we have this number much larger. Okay, and this looks like it is, let's see, 131,010,048. And then we'll do it again for 12, and you see that of course we're getting now to where the numbers are so large to where we're starting to use scientific notation here. So this is 4.17636 times 10 to the 9. And then for 24 hours, of course, this is 1.0266 times 10 to the 19. So it's like really large amounts of bacteria there. Okay, so that's what we would put here. And so part of what you're asked to do is to compute these numbers. So I'm just going to go ahead and run from the beginning and list them all again. So that will be 363,9168. And then we'll do it again at 10. And we got the 131 million. That will be 10,048. And then at 12, we had 4.17636 times 10 raised to the 9. And then for 24 hours, we just plug in 24, and we get 1.0266 times 10 raised to the 19. Okay, and so that is the amount of bacteria that you have. Now, I'm going to do one more of these samples just so that you see how to get the rest of the numbers here and how to go about changing things in your calculator. So let's say now what we want to do is we want to look at bacterial culture number 4 here. So to do that, let's go back to, let's do second quit, and then we need to figure out what is going to be the common ratio this time. Okay, so here I'll make a little separation here. And so now if we take 204 and divide that by 17, let's see, 204 divided by 17, and we get 12. Okay, and so if we do it again using 2,448 and dividing it by 204, we should see that that is 12 again. And you see that it's 12. So of course the rest of the numbers here will follow suit, and the common ratio will be 12. So because of that, we can come here with our formula. A sub n is a sub 1 times r raised to the n minus 1, where the a sub 1 in this case, of course, is the first term in the sequence, would be 17. And the r now, which is the common ratio, would be 12. And so now your geometric sequence formula would just be 17 times 12 raised to the n minus 1. And of course, again, we'll figure out what's happening at the 8th hour, at the 10th hour, at the 12th hour, and then at the 24th hour. So now with our calculator, we can come in and just hit clear. We'll go to y equals, and we'll change these values here. Instead of 13, now we'll have 17. And instead of 6, now we have 12. And since this is going to be an extra number, we want to do the 1 and then hit second delete to insert a number and get 12. And you see how it moved everything over. So now everything is the way that it should be. So now we just tell the calculator to calculate again. So go to second, calc, and then here, value. And then from that point, we're just going to plug in values. So for 8, you see that we get this number here. Of course, that looks like 609,140,736. And then we do it again at 10. You see we get this number here. We do it at 12. Enter. Get that number there. And we do it again at 24. And we get that number there. And so for the first part of this project, that is pretty much what you're doing for all 5 bacterial samples. You're just going to go in and find the formula, depending upon what the first number in the sequence is and the common ratio, and then you just find out at year 8, year 10, year 12, year 24, what those new bacterial amounts would be. Now, please notice that the numbers that I have here are different than the ones that you will have in your particular project. So don't use my numbers, because if you use them, then your values are going to be incorrect. So please use the numbers that are actually given to you in your project. Now that that's finished, the second part of the project requires that you write a report. And so that report asks you to do things such as, number 1, report, show your calculations that you've done, and you can kind of do like how I've done here. Kind of start off showing what the calculations would be, and then just kind of say, hey, I use the calculator to do the rest. And then you want to answer other questions like which strain of this bacterial sample here, and this is supposed to be bacterial, E. coli bacterial, had the highest growth rate. In other words, which had the highest value of R, which one had the lowest growth rate, which one had the lowest value of R, or the lowest common ratio. And so then you have some other questions that you need to answer that have something to do with the danger of kind of bacteria growing and how it may affect humans. And you have some other questions there that are kind of open-ended that you can answer. So here, this is just for the computational part, because I think most of you that may be doing this, it may be this part that's actually kind of keeping you from being able to get started. So I wanted to prepare this so that you could get started. And now that you have this, you can kind of do the rest of the project, do some critical thinking, put everything together, and everything should work smoothly now. So I hope this video helps, and let me know if you have any questions. Take care.